Hello and welcome to today's lesson looking at terminal velocity. Now today's lesson forms part of the AQA separate science course in physics on the forces module. So in today's lesson we're going to look at the forces on fallen objects and describe them. So we're going to describe the forces acting on an object falling through a fluid, relate how objects fall to the forces that act on them and how they change in the fallen object's journey, and then explain the motion of an object falling through a fluid by considering the forces acting through all phases of the motion. So as we mentioned before, this is part of the AQA separate science course in physics in the forces section, which is in the specification point of acceleration. Now it's interesting to note that the bottom points, which are draw and interpret a velocity time graph for objects that reach terminal velocity and interpret the change in motion in terms of the forces acting on an object, are separate science content only. So that will only come up in the separate science examination, not the combined science examination. Now, we can use a velocity time graph to work out if an object's accelerating by looking at the gradient of the graph, and this then allows you to determine if an object has a resultant force acting on it. So let's take this particular graph here. So with the straight line section there's a constant gradient, and the flat line section there's no gradient. Now if you can remember, the gradient of a velocity time graph gives you the acceleration, so therefore that tells us in the straight line section when you've got a constant gradient you've also got a constant acceleration. But in the flat line section you have no gradient, so you have no acceleration. Now we learned this previously, but the only thing that could produce an acceleration is a resultant force. So this tells us that there must be a resultant force in this straight line green section, whilst in this flat line blue section there's no resultant force acting on the object. Now we have to consider a velocity time graph for any journey, but there's one type of journey which is really common on examination style questions, and that's a velocity time graph of an object falling in a fluid. So an object falling through a fluid, which is a liquid or a gas, initially accelerates due to the force of gravity. Eventually though, the resultant force will be zero and the object will move at a constant velocity, which we term the terminal velocity. Because if a falling object has no acceleration, it reaches maximum possible velocity for when it is falling, we call that constant velocity the terminal velocity. So let's just clarify what we have learned so far. For an object to accelerate, which means to either change speed or change direction, it must experience a resultant force. We call that Newton's first law of motion. Now, when an object falls for long enough, the fluid resistance acting against the motion will equal the weight acting towards the earth. This would mean that there's no resultant force because this fluid resistance will cancel out the weight force, so therefore there's no overall resultant force. The object would not accelerate, it stays at the same speed, it moves in the same direction, it's achieved terminal velocity. But there are actually three stages to any fallen object's journey. Now when an object first falls, the weight is larger than air resistance. This means there's a resultant force downwards, so we have an acceleration downwards. Now this example we're going to look at in this lesson is of an object fallen in air, which is an example of a fluid. Any gas or any liquid is a fluid. Now the physics discussed here is also true when an object falls in any fluid, so oil or water. Okay, any particular fluid this physics works for. Now the general name for any force opposing motion in a fluid we call the resistive force. So in air, air resistance acts as the resistive force. So if we want to use this some general names as opposed to the particular ones of a object falling through air, we've got the motive force which causes motion, and we've got the resistive force which opposes the motion. So we have the weight, the motive force, being larger than the resistive air resistance force, so we've got a resultant force downwards, and the resultant force causes acceleration in the direction of the resultant force, which, like we said before, is Newton's first law of motion. So the object will accelerate downwards as there's a resultant force downwards. So we can see that because weight is larger than air resistance, we have a resultant force due to this. So the effect of gravity, which produces weight, would want this acceleration to be 9.8 meters per second squared, because that is the acceleration due to gravity around the Earth's surface. So if an object accelerates only due to the force of weight, we say the object is falling freely or in free fall. Now, Unfortunately, as this object is falling on Earth where there is air resistance, the object will always accelerate at a slower rate than this, since acceleration is directly proportional to the resultant force, and the resultant force is not just the weight, but it's the weight and the air resistance. And because the air resistance acts against the motive force of weight, this means the resultant force is smaller, which means the acceleration will be smaller than 9.8 meters per second squared. So, what do we have in our velocity time graph for this first stage? Well, we've got a constant acceleration downwards, so we've got a straight line as such like this. Constant positive gradient, constant acceleration. But as the object's accelerating, it's increasing in velocity. So this means that the resistive air resistance is increasing because more air particles are being pushed out of the way every second by the object as it falls because it's falling faster. So as a result, the air resistance increases in size. This produces a smaller resultant force and therefore a smaller acceleration. So as we can see, the weight has not changed size, but the air resistance has gotten bigger. So as a result, this resultant force, the difference between the two, is now smaller. So the object is still accelerating because there's still a resultant force, but it's accelerating at a slower rate. Now remember, the resultant force and the acceleration it causes for an object are directly proportional for an object of constant mass, which this is, okay, which is Newton's second law of motion. So as the resultant force is decreasing, the acceleration it produces is also decreasing. Now when you're doing this question in an examination, don't forget to talk about this stage in the fallen object's journey. Every student seems to remember stage 1. Every student seems to remember stage 3, but very few students discuss stage 2. So if we look at this on a velocity time graph, we've still got acceleration, so the velocity is still increasing, but it's increasing at a smaller rate, so it's curving now. So we've got a line curving for this second stage. So the gradient of the line is decreasing because the acceleration will be decreasing. But the velocity, remember, is still going up a bit at a smaller rate. Eventually, we reach stage 3. That's when the air resistance is the same size as the weight, so the velocity of the object stays the same. We call that terminal velocity. So once again, the weight hasn't changed size, but the air resistance has increased now, so it's the same size as the weight. So there's no difference between the two forces, so there's no resultant force, the object is not accelerating, and when there's no resultant force on an object, the object has no acceleration, it maintains the same speed with the same direction, so the object is already moving, which it is because it's falling, it will keep moving. Now this principle in physics is called inertia. Now when there's no resultant force on an object maintains a constant velocity. That again is Newton's first law of motion, just said in a different way. So we can show it on the velocity time graph now because we've got a flat line. Now what does the flat line mean? Well, the line has a gradient of 0, so there's no acceleration. But note, this line is not on the x-axis. That tells us that there is a non-zero velocity. It's still actually moving. It's just not increasing its speed. So it has a constant velocity which is not 0. It's terminal velocity. So at this point, there's no resultant force. The object's not accelerating. So remember that when the object falls, the force of weight is staying constant because that's produced by the gravity of the Earth and the mass of the object, both of which don't change in the journey. It's the resistive force which is changing size at different parts of the journey. So let's just talk about these 3 stages of motion again. Stage 1, when an object first falls, the weight is larger than air resistance, so there's a resultant force downwards, so the object accelerates downwards. Stage 2, as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way every second, so it decreases the resultant force and its acceleration. Finally, stage 3, the air resistance will eventually be the same size as the weight, so the velocity of the object stays the same. That's terminal velocity. Now let's just clarify a few things. Remember, these stages are true for an object falling in any fluid, whether it be air, water, oil, any type of fluid you could think of, any liquid or gas. Now if the object is falling through a liquid instead of air, a gas, The resistive force generated by the liquid is larger as there are more particles densely packed compared to the air, so it's more likely to collide with the object to generate a resistive force. This means a fallen object reaches stage 3 faster. So this means a fallen object would need to fall much further through air compared to water to reach terminal velocity. So objects reach terminal velocity faster in liquids than they do in gases. So let's summarize what we know about motion so far. That velocity is a speed in a given direction. Acceleration is the change of velocity per second, measured in the units meters per second per second. We can work out acceleration with the equation acceleration equals change in velocity divided by time taken. Deceleration is the change of velocity per second when an object slows down. The acceleration of an object can be calculated from the gradient of a velocity time graph. The distance travelled or the displacement of an object can be calculated by the area under a velocity time graph. And you've got to be able to draw velocity time graphs, calculate accelerations from the gradient, and work out the displacement and distance travelled from the area under the line. Now, an object falling through a fluid initially accelerates due to the force of gravity. Eventually, the resultant force will be zero and the object moves at its terminal velocity. The terminal velocity is the constant speed of a fallen object when it's been fallen for a prolonged period of time. Terminal velocity occurs when the air resistance and weight are equal in size. The air resistance will vary throughout the journey, but the weight stays constant. So if we've learned in today's lesson, we can describe the two forces acting on an object falling through a fluid. We can relate how the objects fall to the forces that act on them and how they change in the fallen object's journey. And finally, we can explain the motion of an object falling through a fluid by considering the forces acting on them through all phases of motion. Thank you very much for listening to today's lesson. I hope you've enjoyed this lesson on terminal velocity and have a lovely day.